Suppose you have an exothermic stirred tank reactor, as you can see here. The inlet flow has some concentration of A, let's say that's concentration C underscore AI. Then we have some concentration of A in the exit flow, let's name that CA0. Our goal with this cooling water valve, we can see here, is to control the amount of reactant A that's in the outflow of the reactor. We also need the cooling water valve to make sure that the reactor does not get too hot, since it's an exothermic reactor. So we do not want a runaway reaction. In this case, concentration of A in exit flow is a normal operating control variable. You want to control the concentration coming out of the reactor, but we also do not want the reactor to get too hot, so that's our abnormal control variable. So we're using some sort of analyzer or some sort of instrumentation, AT, to measure the concentration of A that's within the reactor. If we assume it's a perfectly stirred reactor, wherever we're measuring the concentration within the reactor is going to be the same concentration that's coming out of the reactor. Then our abnormal control variable, which is reactor temperature, is measured by some temperature instrumentation. So since temperature is our abnormal control variable, we want to override controller for it. Since we don't want too high of a temperature, we want a high set point override controller. And since if we increase the cooling water valve, we decrease temperature, therefore we have a negative gain, and we have a high set point override controller. So we go to our gain and set point matrix. Since we have a negative gain and a high set point, we need a high select function block, as we can see in this diagram here. We also have a disturbance variable of reaction inhibitor, which inhibits the reaction within the process, and if we add more, it's not going to change temperature. However, it will increase the amount of concentration of A in the exit flow. We also know if we increase our cooling water that's going in the reactor, we're going to decrease the amount of reaction that's occurring within the reactor because the temperature decreases. Therefore, the concentration of A in the exit flow would also increase. We'll now walk through two cases. The case one involves increasing reaction inhibitor and not having an override temperature controller. Case two has the identical increase of reaction inhibitor, but there is an override temperature controller, which makes sure that the reactor does not get too hot. So let's talk about this first case. So we have 4 dotted blue lines, and these are initial conditions or set points. It's the first dotted blue line, as we can see here, is the high set point for the temperature override controller. This blue line here is the set point for the concentration of A in exit flow. This blue line here is the initial condition for a reaction inhibitor. And this fourth blue line is our initial condition for the cooling water valve output. Then each vertical red line is a different sampling period. T1 is sampling period 1 and sampling, so each sampling period we're measuring or we're controlling some sort of action. So suppose at T2 we have a step increase in reaction inhibitor. We know that this will increase the concentration of A, and since there's going to be an error between concentration of A and our set point, we know we're going to want to decrease the amount of cooling water so that our concentration of A goes back to set point. However, if we decrease the amount of cooling water, we also know that we'll increase our temperature. So since we are decreasing controller valve output, our temperature is going to be increasing. And in this case, it crosses the set point, but since we do not have a override controller enabled or configured within our DCS, then the temperature is allowed to exceed its set point, which could potentially cause a runaway reaction. So now, just assume that there is a temperature override controller for the reactor. So again, at time or T2, we have a step increase reaction inhibitor. This would naturally cause a cooling water valve to start decreasing because the concentration of A increases. However, at T3, we can see that the temperature exceeds a set point. Therefore, the temperature controller will now be controlling our cooling water valve output. So now we can see that because our temperature is above set point, our cooling water valve will start increasing again until our temperature converges back to set point, which causes our concentration of A and exit flow in our exit flow of our reactor to have some delta between its set point and its PV. Oh, I did not want red here. Let's get a different color. Let's get white. So there's some delta between set point PV, but the temperature of the reactor is priority since it protects the equipment, while we can live with some more concentration of A and exit in the exit flow. So this shows the importance of why you need override controller and how there is going to always be trade-offs between, hey, if an abnormal condition occurs, then we got to protect the equipment over protecting costs or whatever the normal operating control variable is being used to control. As if safety will always supersede quality, as we can see with this example. So thanks for watching. I hope you all have a great rest of your day.